Hello, Sarah. Hello, Kay. Hello, Lola.
Hi, Dr. Kivin.
Hello, Dr. Klee. Hello, everybody.
Hello, Lina.
Hello, Lina.
Hi, Lina.
Hello, Steven. Hello, Boston. Okay. Thank you for connecting and for your dedication to the class. Thank you for tolerating me and being patient with the homework, which was objectively heavy, as I noticed. I have very ambitious plans, and I already know that I will not be able to fill them in today, but I'll try my best. So I did send slides from previous years, but I'll try to go straight without even talking.
I just connect.
Yeah, that's good. That's good. Thank you. So there are 5 goals, and it is probably a larger number than I can carry in the head. So I hope better write on the board. So on one hand, we need skills practiced on Portal. But at the same time, since the Photon will not accommodate 2 large systems, we need to do it on NERSC. So, and basically, everything we practice on Photon, I want to duplicate and show how to run it on NERSC. And this will slow down all process of demonstrations and checking about 3 times. So if you are not very ambitious, if computational chemistry is not your life goal, you can stay within just practice with something important. But if you really have plans to do productive research, then duplicating processes, everything I'm sure on NERSC is critically important, because even those of you who are practicing CCAST may have noticed that sometimes it is fails to do some jobs. If you didn't, maybe your models are not big enough. But NERSC is not solving all problems on the globe, but it is a little more powerful. Another thing we will need for the project. So this stuff on NERSC is optional. That's very recommended. And then on your personal computers, you need to do visualization of what's this GMT software. I will fail to demonstrate it today, just because time is up. But by the next Wednesday, please make sure that I know it was part of the homework and you reported. Some of you did made a screenshot of VMD button on your desktop. But make sure you can open software and open some files there. Next Wednesday, we will do it practically, and it will be not possible without it. So it will be critical. So it's really, so our main goal that I will do at any rate is to practice invisible surface. And it will be done for the model that we did in the previous lab here, like for titanium dioxide nanowire. And your homework, I'll meditate a little bit, and I'll assign it on Friday, but it will include to do UV visible absorption spectra for your other models that you love so much. Okay. So this is for sure spectrum component, and if time allows, is to do the same absorption spectrum on NERSC as well. The transmission of files between photon and NERSC will be, I wouldn't say impossible, but it is a little painful, not painful, delaying. So recently, originally we all learned to transfer files with SCP command, but recently there was a little bit of simplification. We were able to just use buttons with click and drag and drop. For NERSC, they will not allow this stuff. We will need to do SCP. And it is a price we pay for high power of this stuff. The commands are similar but not identical, so it will be a little delay. So by the time we finish these two things, probably it will be, everyone will be tired, and we will need to locate and relax. But next step that I want to start today, if time allows, is to go towards the concept of thermalization. And oh, nice seeing you with camera. So heating and molecular dynamics. So those things are highly efficient. They help to model like docking, chemical reactions, but they are more expensive than stuff that we did before. And we can start doing them on photon, but for sure they need to be practiced on NERSC. And now it is only an outline. We will go into details, but the main thing, one, and I will repeat it maybe 10 times during the main course, molecular dynamics cannot be run without heating. And heating and molecular dynamics are two different types of job. So before one will be able to run molecular dynamics, one needs to start heating. And yes.
So heating means temperature dependent.
Yes, it is thermalization. It is assigning velocities to each atom.
Yeah, so more interactions and more, so
Yes.
more complicated.
So it's not complicated for humans, but it is much more time demanding for computers. And maybe if you can run at least one heating job on photon and on NERSC, it will be a good preparation for our next meeting.
So that means that the processes or the calculations we're using other softwares could be achieved at 0 Kelvin, for example?
Molecular dynamics.
It's
Time
independent.
Molecular dynamics at 0 Kelvin doesn't make sense.
Okay, so is it
As soon as something is moving, temperature is bigger than 0.
Is it when we started talking about shooting the recursion time dependent and time dependent using or I guess. So is it depending on solving the equation? Dependence reading the equation?
Thank you. Your question is correct.
Okay.
But the answer is more detailed.
Okay.
And
I didn't get the announced course.
so Lila did ask more details, more clarification about molecular dynamics. And her question was, does it deal with time-dependent Schrödinger equation because time is involved? And the answer is more no than yes, because before we start these things, and we will start them at the end of today's meeting, and then the next lab will be dedicated to them. Before this meeting, we have forgotten everything we did in our first months of the lectures, when we were considering nuclear and alpharic degrees of freedom. As soon as we practice molecular dynamics, we allow nuclei to move. So it will be Schrödinger equation coupled to Newton equation of motion for ions. Make sense?
Yeah.
And if we launch heating and problem molecular dynamics jobs today, then they will be done by next week, and we will be able to analyze them. And I realize that these ambitious plans are wishful, but maybe hard to complete. But it's my plan. And then VMD is the best tool to analyze results of molecular dynamics. So if you experience difficulties in installing VMD, let me know ahead, so we can solve it cooperatively before next lab. I have some backup solutions, but they are not evident. There is nothing better than VMD. So please log into your start the mobile external, log into Photon servers, and for the first hopefully 45 minutes, and practically it may take even up to the whole meeting, I am going to obtain the following 4 figures. So I will just speak about them and to entertain you and satisfy your curiosity, but please better only if you already logged in. So life is not a village. I'm trying to avoid writing equations and discussing. Some of you have, well, all of you have submitted notebooks. Providing answer to the last 2 questions with different level of utilization. The second last question about equations for transition dipole was intentional. It was a path to today's lab. So the figures, 4 figures that I'm going to show, they illustrate ability of a molecule to absorb light at certain wavelengths or at certain transition energy. And if you do wet chemistry synthesis and characterization, you may have seen this spectrophotometers or read about them in articles. Some labs involved in, and some of you are doing in your practical research. So the question is to screen all possible transition energies or all possible excitation energies and see at which transition energy system absorbs better, at which it absorbs worse. So the energies at which these peaks happen, they are equal to difference between orbitals, orbital energy. The lowest transition is energy difference between coma and coma that you are finding in the labs and homeworks. And amount of these transitions is much bigger than the amount of orbitals, because it is basically number of orbitals squared, number of occupied times number of unoccupied. Between each orbitals in those pairs, transitions are possible, but some of them are efficient Some of them not. So the height of the peak is different. A lot of experimental community prefer to do this plot in the wavelength series. So if you notice, in previous plot, we start x-axis from 0 in the order of increase. So energy increases, frequency increases. And wavelengths are inverse units. They are energy divided or constant divided by energy. Right? So infinite large wavelengths means zero energy. So one should going backwards on this nanometer axis is increased energy. So this is the first peak. And then one goes like from red to blue, and there are additional peaks of different height. I do have intentions to discuss equations for this stuff, and it is not complicated, but we better focus on practical side. And same peaks, same spectra for the same system can be, here I'm showing them computed on photon and on NERSC. And this one is also as function of energy, just a little narrower window. So first peak is around 3.2, 3.3, right? And then there are some peaks of different intensity, and one can also represent it in as function of nanometers. So I'm going to show practical steps how to arrive to these figures. And if you are part of the homework for the next weekend and beginning of the next week until Wednesday to compute the same style of figures based on the models, the same models you practice now. Some of you did receive comments from me about your homeworks, even if homeworks were getting high grades. There were some constructive criticism. So while going towards the next homework, if you want, again, my main goal is to check that you will be fluent in practical steps. But if you care about the scientific correctness of the results, you may do additional steps towards improving of the models. For example, in some of the homeworks, I noticed that elements were swapped. So while building pod car, one swapped silicon and hydrogen, and then it was WASP does not forgive some questions, such errors. So, for example, in silicon nanowire, if you swap silicons and hydrogens, then the backbone in the center will be hydrogens, which themselves are not happy to bond to each other, and the wiggins on the side or silicons, which were not compensated by additional hydrogens. So such system will predominantly have no gap, which differs from experiment. It will show metallic behavior while silicon is expected to be semiconductor. So to the next homework, you can revisit and improve. Another thing, I was skipping the procedure of optimization for the models because I didn't want Steven to get angry at us for overusing the photon. And same for molecular dynamics. So for educational purposes, we can run a little bit, but for productive, let's use NERSC. So after the model is built, one can directly go into electronic structure, but in between this, one can run a job for optimization. And if atoms are coming into optimal configurations, the bandgap and other observables become more realistic. So if you have energy and steam, you also can try to re-optimize your models towards that forward. Again, it is not the main task. I will be checking primarily your ability to generate absorption stuff, but for little training you can practice. So let me share screen, and if I will try to practice same style as before, showing something and circulating the sheets and asking those online to share screen. But if I forget to do something, do not hesitate to attract my attention. I can get too excited with typing commands, so please help me to stop focusing on the computer rather than people. Yeah. As we go through practical side, I'll refer to the slides and give some additional explanations, but right now let's go directly to the practical aspect. So I did log into Photon and created a directory for lab number 9 and subdirectory ABS for absorption. I'm going to repeat all steps so that you will see that nothing is set up. So absorption B. So in this directory, I do need a couple of files from my previous run. So from lab 8, I do need the states. So it is the directory where I was doing the titanium dioxide nanowire, where I was doing the density of states and the orbitals. So although I will not directly use it, but I can copy input files. Oscar. Oh. Oscar. So the computation of absorption structure does need information about orbitals, as you were writing in your homework assignments, right? So one needs transition dipole, one needs oscillator strength, which depends on transition dipole. And I see that these words may scare some of you or bring you out of the comfort zone. So show me signs if words transition dipole and oscillator strengths are okay or not okay. Okay, more or less. Lola, is it okay, not okay, or more or less?
I didn't hear what you said about transition dipole.
Does the word transition dipole, so do you feel comfortable with this word? Do you know what it is?
No.
Okay, so at least in the lecture number 16, when we were considering observables, we were looking for the matrix, transitional matrix element. We were looking on the interaction between light and matter, and we were looking on how the system comes from ground to excited state. And in order to evaluate intensity, we were putting the transition dipole in between them, right? So it is what was what you were invited to write in the last homework. So this transition dipole does depend on orbitals, right? It includes orbitals. So orbitals are saved in the file wavecraft. And we will use them not in the nice graphic form as you were showing in your homework, but it will be used in the computer style file. Do not try to look inside this file. It will bring a lot of garbage to your screen. It is not readable by humans. But we need to read this file and practice transition dipole calculation. Let me check. Maybe no, I'm skipping this equation. Maybe I'll write it today, but I want to be quick in practical things. So I also need states. So practical steps. First, I copy states into file under different name, energy and population. Then I count number of lines there. Then, if I do not trust my memory, I look at my cheat sheet. So here is the code that converts the list of orbitals and wavecar file into information needed for absorption spectrum. If I hit enter right now, it will bring me an error because there is no input file. So before I practice this code, I need to create a third file, which with name input overlap. So the total number of orbitals here, they go from 1 to 39 for this specific system. So I create file VI input overlap. First line 1, second line number of orbitals, third line 1, which means nothing. It's just I was lazy to change the code. It was used before. So file input overlap is here, and after that, I execute this binary oscillator strength dipole version 3, and it starts bringing some information. And upon completion, it reports that things are done. So ls-t, there is a new file called oscillator strengths, and it is about, for this system, it is about 20 kilobytes, so 20 times bigger than the state. So please try to follow these lines, and I will circle around and then ask you to share screens one by one so that we all are on the same page. So we co-host. Host. And let me bring to the file input overlap, and the command is this one: binary oscillator dipole.
Well, I did the file, but
Just
confused.
which one? Just try. Why?
To try to copy the.
Oh, I'm a team work. I don't know what this was. I think it's one RH. I haven't finished it yet, but I'm very much to like boards. Reading through it and then five might just over with. Yeah. I shot yet, so that's for sure. We're talking about that, but oh well, we'll see. I'm good. I think that one should just be. Think.
Okay, you
You just use the same equation. All zeros. A at corner, I have to figure out what K is, but it would just be one K and points to the corner, one K that points to the. That's just reading it real quick. That's my intuition, but I could be wrong.
Really just these two commands, nothing else. Let's start sharing screen. Kay, would you like to be first? I don't hear.
There's some problem with my microphone. Just a minute. Yeah. Professor, are you able to see my a screen.
Okay, yes, I see. I see. Can you please type PWD?
Okay. PWD. Right?
Okay. Can you type LS?
Enter.
Enter.
I already copied, but then I
I
missed.
see. What is your states file? Please copy states file that you used for the density of states.
Oh no 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 no.
Do you have in a different directory?
No, it's the
Maybe
same.
it's different in Lab 7 or.
Okay, in a lab 7. Oh God. That 7, I guess. So,
More space states. States. Enter. Space.
Okay.
CP.
CP
Space. States.
states.
Space. Lowercase energy.
Lowercase energy.
Energy. No, not lesser, just energy. Type the word energy, underscore POP.
Underscore POP.
Lowercase POP.
Okay. POP.
Enter. Okay, WC space
States.
energy underscore POP.
Okay. Energy. Okay. Enter.
Enter. Okay, VI space lowercase input underscore overlap. Input underscore overlap.
Lab.
Enter.
Then one
Letter I. 1.
39.
Enter. 39.
1.
Enter. 1. Enter. Escape colon WQ.
Yep.
Enter.
Yes.
Tilde.
Yeah. Just
The wavy line.
yes.
Slash bin. BIN. Slash uppercase OS.
OS.
Underscore dipole. Lowercase DIPOLE. Underscore V3.
V3.
Lowercase v and number 3. Version 3.
Okay. Done.
Enter.
No.
Okay. Arrow up. Delete couple of just delete couple of symbols at the end. Backspace. Hit tab button. Hit tab button. Tabular. Tab, yes. Now type letter V, lowercase.
D.
V.
V.
And hit tabular once again. Enter.
Okay.
Now type ls minus ot. Ls space minus ot. You see there is a file os underscore strengths.
Yes.
And you can type more space os underscore strengths.
This one? This command?
OS uppercase OS, no, O uppercase OS underscore strengths. Uppercase strengths.
upper.
It's the third file in the list. You
Yes,
see,
yes,
and hit tab. It will automatically continue. Strand
Oh, no, 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 no. Tab.
N
Yes.
G T H.
Hmm.
Enter. Okay, you're good. You can stop.
Just one question here. Let's go. So this OS strength, it's
I will explain what it means. Let me check that everyone obtains it, and then we'll discuss it.
okay. OS strength, then energy pop. I don't know what is this. Okay.
I'll give comments what they mean. I'll just rush so that everyone can practically get them. Okay, thank you. Lola, would you like to share screen?
Yeah.
Okay. LS, please type LS, enter. CD, go into the directory where your files are, ABS or ABSB, whatever you decide.
It's empty because I couldn't.
Okay, then we'll populate them. So
I couldn't copy. I don't know. I think I checked lab 8. I don't think it contains what I need.
let's do it together. We'll find it out. If not, we'll just recompute. It's a matter of a minute. So please hit arrow up. Arrow up. Stop. Backspace. Backspace a couple of times. Now hit tabular button, tab, on the left of your keyboard. Up TAB. You see there is a next to the Q.
It's not doing anything.
Okay, then Control C to stop it. Control C or just backspace everything. Type LS space, no, LS space, do enter, double dot,
Double what?
double period, just
Okay.
repeat the same thing as in the previous line, period,
Okay.
slash, period, slash, lab 7, slash, enter. Can you please type PWD? Enter. Okay. Yeah. So let's go to, oh, your lab 7 starts with uppercase. You see some of your labs, some
Yeah.
of the directories start with lowercase, some with uppercase.
So, okay, I need to go back to lab 9. Slash, right?
Yes, and not CD, but CP. You can do, you're not, CP, yeah, now go to the end of the line. And check if states, or you can, states, space, period.
Should I write it again?
Can you share with me, can you permit me to type something on your computer?
Okay.
I know you are teaching me how to do it, but I have forgotten. And let me know when it is. When
You
are-
can. I've allowed you.
No. Oh, okay. So let's check what is in your web 7. There should be state because I see this DOS Fermi file.
Can I check lab 8?
By some reason,
Oh.
maybe.
The states, I mean, yeah, the states.
Oh, it is here. It is here. Good.
Yeah.
We have states. No, not ls. We need to copy. Copy. And we also need the wavecar. And just in case, we can copy postcar. And keep. Just in case. Okay. So I think it would be more helpful if now you type yourself, so you can withdraw privileges from me. And now please start copy CP space states. CP space states space lowercase energy underscore POP underscore POP. Enter. VI space input lowercase input underscore overlap input underscore overlap. Enter. First letter I to start inserting. 1, enter. 39, enter. 1, enter. And now escape colon WQ. Okay. And now tilde, the wavy line, slash bin binary slash OS.
Sorry?
Uppercase letter O, uppercase letter S. OS underscore dipole, DIPOLE underscore letter V and number 3.
Did you say D as in dog?
No, V like Victor. Lowercase. Enter. Let's arrow up.
The dipole should be without the E.
Maybe let's do uppercase. Upper arrow up. Erase. Yeah, try. Yeah. Oh, okay. Now do ls space minus LT. Enter. So you see the third file in the list is OS underscore strings. Yes. Can you please type more space and then name of this file? Enter. Okay, you're good. You can stop sharing.
Okay, thank you.
Thank you. And Sarah, would you like to share your screen?
Yeah. Dr. Green, first I have a question. Which outcar file we should copy? The one in the lab 8, which doesn't have orbitals, or the one from lab 7B, which has the orbitals?
The out car that has orbitals.
Okay. So for me, I face an error.
Not a problem. We will fix it. Can you type ls? Enter. ls minus ot. ls space minus ot. Enter. Okay. More space energy pop. Space energy underscore pop. Enter. Space. Okay. vi space input underscore overlap. Overlap. Enter. Letter I. Number 1. Enter. 39. Enter. Number 1. Enter. Escape. WQ. Enter. Arrow up. Arrow up. Arrow up. Arrow up. Arrow up. Enter.
Oh.
ls minus ot. ls space minus ot. You see the file number 3 is os underscore strengths.
Yeah.
And type more space os underscore strengths. Enter. So you're good. You can stop sharing.
Thank you.
So you have received this.
So, Professor,
yes.
When I copy the outcar file, I copied from the lab 8 and that has no orbitals. So I need to copy that one from the previous lab, right?
Well, as long as you do have states, it doesn't matter.
Okay, then it's fine.
We are just copying it as a backup. Cert use line. As a little relaxation, I will speak about this file. So you probably see about 9 columns, right, in the file, and we didn't practice votes on who present what during presentations, but the one who will select UVS spectra is expected not only to share practical things, but also explain what the data means. So here are verbal explanation, and I'll probably write one, repeat the question from the lecture 16 and from your homework. So columns 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first and second are initial and final orbitals. So it is orbitals between which transition is happening. Columns 5 and 6. So column 5 is associated with column 1. So it is amount of electrons in orbital that is in column 1. 2 electrons. Column 6 is amount of electrons in the orbital listed in the column 2. So 0. We look for transition from orbital with 2 electrons to orbital with 0 electrons. Right? Now, the column number 4 is, so if you call this one as I, this one as J. Then we can define energy of empty orbital, energy of filled orbital, and this energy difference will be stored in the column number 4. Transition energy that we list along x-axis when we do spectrum, right? The third column is most important, is so-called oscillator strength for pair of orbitals Fij, and it corresponds to the height of the peak, right? The bigger the number in column 3, the higher the peak. And it doesn't need to be tall. Some transitions are, if the peak is high, we tell that it is a bright transition. If it is close to 0, we tell that it is dark transition. Yes?
So does that mean it's more likely to absorb
Exactly.
the light the higher the peak is?
Yes. So, and the remaining peaks, remaining columns 7, 8, and 9 are projections of transition dipole. Yes.
But if like
There are no stupid questions. There are stupid answers.
if the oscillator strength is it like a linear relationship? So like if one has a strength of 2, another has a strength of 4, is the one that with strength 4 twice as likely to absorb a photon than the one that was 2?
Mm-hmm. And the data in columns 7, 8, and 9, they are often not needed. They are intermediate data which help to compute oscillator strengths. Technically, the dipole, which sometimes called with letter D or sometimes called with letter mu, J, mu, J, is integral of phi I r phi j dr, right? And since it is a matrix element of a vector, it has 3 components, x, y, and z, and they're stored here. And oscillator strength is approximately equal to j absolute value squared times some constants. So if we look for properties of materials that are homogeneously spread in like solution, then there is an orientation average, and we need average oscillator strength. But if you are if you have some anisotropic material, if you have crystal where absorption along one axis and another is not equal, then one may come back to this data. So it's for 99.9 applications, it is not needed, but just in case we keep them here. And basically, well, I already drew it, but let me offer the question that the one who will select the subject for presentation may offer it. So absorption at frequency, certain frequency, is computed in a similar way as we do density of states. So oscillator strength times delta function, which may have we may assign it artificial width, and here we have this frequency minus energy difference J minus E I. Okay, the oscillator strength itself is equal some factor times C times D X Ij squared plus d y Ij d Ij, and the d Ij is integral phi I j. Okay. So it's just if you have curiosity what we are doing. So we are putting this stuff. Okay. Yeah. So height corresponds to Fig, and the position corresponds to energy J minus energy I. Yes.
Just before going to the next step, so the three values that we put into the input overlap file. So we how we choose these numbers?
First orbital, last orbital, and the number 3 is always 1. So
it was for our model 1, the first number.
First orbital, 39 was the last orbital, and 1 is always 1. Okay. Thanks for checking it. So spectrum improved version 3. Tilde beam spectrum improved version 3. And it will not work right away. You need some information. So same. I'll stop. When we were practicing to visualization of density of states, we converted discrete list of energies into continuous distribution. Now we do have more or less strengths. So you have discrete list of transitions. So this is transition energy, this is height. So we need to convert discrete list of transitions into continuous spectrum. The procedure looks the same, code is basically the same, and way how we operate this is very similar. So we need to type some input parameters, and one of them is just a summary how many lines are in the oscillator strength file, right? So in order to count lines, I type WC OS strength. So 224 lines. And I think there also it will ask the number of HOMO. And if I have forgotten it, I can scroll through energy pop and see that last occupied is 32. And also some of your questions about last email included request to specify the window, the range of energies in which we plot density of state. So in a similar way, when we convert discrete set of optical transitions into spectrum, we need to specify a window, right? So if you know nothing, if you shoot blind, you can specify from 0 to 10, but it is a little too ambitious. It's just general because there are no absorption below 0, and we don't carry an absorption above 10. But one can also estimate this range by looking on the list of orbitals. So lowest transition will be at the difference of these energies. So minus 3.5 minus subtract minus 7, so about 3. And then maybe we need another 3 alkene volts above. So I can go up to 6, and I can start either at 0 or I can start at from 3 to 6. So it doesn't matter now. Okay, so I think it's enough information. So I'm typing this comment, and last time I have forgotten to share comments in the chat line. Chat line, come on. Everyone, please. So number of transitions, 224. Energy difference. And do not put 0. It should be like 0.1, because for nanometers it divides by difference of energy, and we do not want to divide by 0. So from 0.1 to 10. 4, 0.1, 10. Width of line 0.005. Number of HOMO 32. So after this command ls9t, I am getting a file which is named spectrum. If and you see that it is about 10 times larger than oscillator strength because it has more points. If I hate the plot, I can just download this file spectrum and plot it with Origin or Microsoft Excel. But I'm going to convert it into graphical format with GNU plot in the same style as we did for density of states. I'll probably finish because it's just a couple of lines, and then I might be sorry. So GNU. Oh, what maybe if some of you are.
So what's the previous?
Yes, absolutely. I can even share this one. Copy. Chat line. Paste. Yeah, thank you, Lina. So meters. So I'm going to run a GNU plot command with this couple of scripts, and you see that it just plots file spectrum with lines 2 and 3 and with lines 1 and 3. So line 3 is intensity of transition, line 2 is transition energy, or line 3 is intensity of transition, line 1 is nanometers, not line, it's column. So I'm typing GNU plot. This one, and then GNU plot this one. Share them just in case also in the chat line. And then I can ls -t. So I'm getting two files, spe.ps and sp nanometers.ps, and I convert them ps to pdf wr spe underscore nanometers. Copy. Chat line. Paste. And now I do ls-t. No. And it has this PDF files, which I can go into this directory, absd, and there is file spe.pdf. So it shows first transition at 3.3 thousand volts. And if I look here once again into more strengths, look at the first line. So transitions from HOMO to LUMO +1, 32 to 33, at 3.3 thousand volts, with intensity that is bigger than anything else. So the lowest transition is the strongest one. Well, it is not the lowest. The HOMO to LUMO is, I do not see it in this list. It's somewhere lower. Okay. I'm going to make a circle and make sure that you are comfortable in reproducing this thing.
It's your body, the vertical axis is very calm. So how would it scale that? Because one I highlighted is to
There is an effort to normalize it, so that you will, otherwise, if you take bigger system, it will lower and lower and comparable.
that's all I.
Which is discrete list. Excellent. Thank you. Kay, would you like to share your screen?
Oh, this will stop others. What happened? Continue.
Okay.
So I did this.
And just try to I think the files are ready. Try to download them and show that you can see them.
And what's the command? I forgot.
Let's just move your mouse slowly to the left.
There?
Mouse slowly to the left. Can you move?
This one, right? There?
Yes, and there is a green symbol. Yes, double click.
Yeah.
Double click.
Yeah, I
Click.
already clicked. It's loading.
Mhm. If it does not follow your command, okay. Yeah, type the reconnect SSH browser.
Yes.
Okay, and now double click on this greenish. Now scroll up, double click on green symbol. Now scroll down, scrape, yeah. Cam, yes. Then for year 20, yes. Yes. The lab
9.
whatever you get, okay. Description. And then bring this PDF files.
This one?
Yeah, start from this one and then, yeah, and this one as well. Please don't. Can you open them?
Yes. I think it's automatically open, but oh, there are lots of files. I think this too. No, not this. This one from homework. Oh, okay. Got it. This one and this one.
Okay, yeah, excellent. Excellent.
Done?
Yes. Yeah,
Okay.
super. Thank
Stop
you.
sharing.
You can stop sharing, yes. Sarah, would you like to share screen?
Yes. This is
Okay, yeah, it's perfect. I see it. Excellent. it was really quick. Yes. Thank you. You can stop sharing.
Sure.
Lola, would you like to share screen?
Yes. PDF. Okay.
Okay. Okay, yeah. And yeah, very good. Thank you. You can stop sharing screen.
All right.
So we have completed minimal part of our plan. So we did this we are done with UV visible absorption spectrum on photon, and I think now it will be reasonable to focus on how to do it next, how to do file transfer. So in case you care only about the grade in the course, it will be auxiliary. But if you plan to do research, maybe it's more important than the rest of the things. So if you are taking records, if you have some additional file where you're taking electronic records, you can, just in case, record the directory where you did this little exercise. Just in case if I forget. Now, I am going just CD with no arguments. So be careful. This command will bring me to the root, not to the root, but to the user directory, and it may take then few additional time to come back to this directory. PWD, and now from here. So try to copy paste the command from here. Copy, paste, and I will share it in the chat line as well. So this command brings you to a different server, and they also have tree of subdirectories which are hard to navigate. So I type more war 0. It shows since there are like 20,000 users and several very large amount of accounts, the navigation through directories are a little bit more advanced. So I go to this directory. Where we will start. And there, last time we created subdirectory for the class 2021. Let me copy to the chat line as well. Chat line. Paste. So there, by now, there is subdirectory for myself because I was preparing for our meeting. But you can type make directory and identify yourself in the way you like. I can do it once again for myself. Please try practicing it right now. I'll make a circle so that we are.
I don't think you sent the directory.
Huh?
You just maybe paste that. You didn't send the directory.
I didn't.
Yeah, you didn't. It's not the chat line.
Okay. Yes. I'll probably forgot to hit enter. Check. Oh, okay. Yes. Thank you. Thank you for reminding me. Yes. So I know it's quite a simple task, but I'll make a circle and make sure that we all are on the same page. So what's done? No, don't do this. Do this. It's the second. Sarah, would you like to share screen?
Yes.
Okay, very good. Now type CD space CHEM676 uppercase CHEM676 underscore 2021. Enter. LS. Enter. Make MKDIR and then identify yourself. Okay, enter. Very good. You can stop sharing.
Thank you.
And now go to your directory CD. Sorry. Okay.
Okay.
Very good. And you can stop sharing. Kay, would you like to share screen?
Just a minute. Oops.
Okay. Please type PWD.
Now?
Yes, PWD. Enter. Okay. Arrow up. Arrow up. Arrow up. Arrow up. And enough. Now arrow left many times and to the end of the line, the beginning of the line. Arrow left.
Yeah.
Arrow left. It's not allowing you.
No.
Then just copy this link copy this global CFS CDIRS M1251 was just copy it. Now do no, erase everything. Erase everything. Erase. Further erase. And now type CD lowercase. CD for change directory, and now paste. Enter. PWD, just in case. Lowercase PWD. Enter. Now CD, lowercase CD, space.
Yeah.
And with uppercase Chem 676. 676 underscore 2021. Enter. LS. Enter. MKDIR. Space, and then identify yourself. Yes. Enter. And now CD. Oh, you do LS. Enter. CD space K. Enter. Okay, you can stop. You're good. You can stop sharing.
Okay, thank you.
My pleasure. Lola, would you like to share screen?
Yes.
Thank you. Okay, you are in the year 2019 or 2018. You see,
I don't know how I got there.
Not a problem. Not a problem. So lowercase CD space period.
Should I press enter or C? I mean, I don't
CD
know.
space. Yeah. What was good? CD space. Period. Dot. Enter. Enter. Now CD space.
CD.
CD space. Uppercase Chem 676. Uppercase. Uppercase all 4 letters.
Okay.
Uppercase. 676 underscore 2021. Enter. LS. Enter. And now MKDIR. Space and something how you like to identify yourself. Enter. And now do CD space Lola. Enter. Okay, you're good. You can stop sharing.
Okay, thank you.
So I start sharing again. See. So I am going to my subdirectory. I can create a subdirectory for the lab, and I made a subdirectory for titanium 4 oxygen 8, but I'll make another one. So I want to show the complete process. So create directory, go in there. So now it is an empty directory. So I want to copy here the information from photon. So because of specifics of the server, it is not encouraging to operate it from photon or from another computer. You need to log in there and then you can access photon. So I'm going to copy. I'll share the command. Photon can edu column, and then I return to my records, and I will copy everything. Copy. Paste from there. So, and then I will put star and put period. So basically, I'm copying everything I had in my directory on Photon into here. And after this, it will ask the password for the Photon. So I'm going to copy this command and make sure that you are copying from your directories, not from mine. I don't mind sharing my data, but for educational purposes, you better process your personal data.
Dr. Kirin,
Yes?
sorry to take you back. Why are we importing files into this place? Why are we working on this?
So I'm using the symbol star, which means everything which is contained in this directory. Symbol star means everything. Does it make sense?
Yeah.
So if I would have meticulous personality, I can type here pause car and then enter, and then type the password. And then it will transfer only one file. Then I can select another file and transfer it. But it is kind of silly. I better transfer the whole package.
Yes, okay. So my question is this, when we came into this, we had to type more where 0/global. Like why are we in this? Why are we not working in the usual Photon server?
The question is, why are we using Dars and not Photon?
I can't hear you, Boston.
Lola, did Boston interpreted your question correct?
Are you asking why we're using Dars and not Photon?
Yes. Why are we here?
Okay. Yeah, thank you. So for educational purposes, for small models with like 10 atoms, or it doesn't matter, Photon is strong enough. But for practical problems of that you can use in your research and publish with like 100, 200,000 atoms, Photon will be just burnt out and or will just decline to pick up these problems, or it will compute for a couple of years, which is not acceptable. So we need a supercomputer that is substantially more powerful. Like if you know Linux, on the Photon, if you type commands that will identify nature of the server, or just simply TOP, you will see that it has only 64 CPUs. And by today, it's not a big achievement. So, like most of laptops have like 8 cores or something like that. So it's not super productive. And CCAST has like whatever, couple hundred nodes, about 30 cores per each, which is better than Photon. But NERSC has maybe 10,000 nodes, 64 cores each. So even if they give small share of their resources to us, we can do wonders. So we are going to basically right now for the next whatever, until we get tired. I know that by schedule I have only 10 minutes, but and I will not hold you long. But I plan to show how to do the same things as we did on Photon on NERSC with the small model, with understanding that later on you will be able to use substantially bigger models. So if photon fails, you go to NERSC. For this small practical model, photon will not fail. The model is intentionally selected so that you can get some education with it. But as soon as you get like 200 atoms, which is a typical size for publishable computation, you need to use supercomputer. Well, does it answer your question?
Yes, it does. Thank you.
Okay. Okay. So right now I am on NERSC. I did transfer lots of files, and I want to play fair game. I will do something stupid. I will remove everything .ps, everything .pdf, and I even will remove the states and energy pool. So now I am I'm unprepared. I need to start basically from scratch. Remove spectrum and remove oscillator strength. Good. So I have postcard. We have in-car. So I have clear mind. I just need a few seconds for words. So I do have podcar key points, but I do not have impar. I'm taking it is directories are arranged in a similar way as on photon. So I'm copying the impar geometry optimization into this directory, and I'm naming it as an impar. And let me copy this command. Copy. So the based on the time, I will be able to show demonstration, but I know that you may have schedules for relaxation after hours, so I'll do at least demonstration and then check if anyone wants to answer questions. But I want to arrive to the same spectra as we did before. Okay. So now I have the file in car. Note that right now, since it is a very powerful computer, you can keep this NSW with some noticeable number. If you are doing things on photon, you better have it to 0. Otherwise, it will take too much resources. But this NSW, it tells if we allow the model to be optimized. So if you really go for publication, you need to optimize until it converges. Okay. Now, I do copy the stuff that I just list here, cd bin launch debug sh into here. So right now, this little command that I will share to the chat line, I will bring a very important concept that we never practiced in course, with except of Boston, who taught us how to use CCAST, and Steven, who is practicing CCAST, and some of you may practice it with other software. So on the supercomputer, there are, it's not correct to use the front node and launch executables. It has like a cloud or many compute nodes, and there is a like mid-man or mid-computer scheduler who connects users with this compute node. And there is a list of jobs in the queue. They launch not immediately, but after some delay, depending on how big the job is. And this, the last command that I did share with you, debug.sh, is an interface between us as humans and actual compute nodes. So this debug script allows us to communicate with overall NERC supercomputer system, and we'll, right now we are on like front node number 12, because it's a big supercomputer. It has not one as on CCAST, but multiple. But those front nodes are not assumed to be used for any computation. They are only interfaces, and with this debug.sh, it will transfer us to actual compute node. If more so right now I'm using requesting only one node and 64 cores, all cores available in one node, and I will launch the standard version of Rust. There are some additional versions for optimization. And debug queue means it is not for productive computation, but for some quick tests. So it's short, it substantially reduces wait time. If you go for like day-long computation, we may wait a couple of days in the queue later on. But now those are small systems. So I have all input files, and I also can remove wave car if I want, because it will be redone. And now the most important command is sbatch debug sh. I'll also share it in the chat line. So it tells that this job that I submitted is job number 41,017,391 since launch of this computer. So you see that we are not the only people who use it. And I want to know whether this job is being run or it is pending in the queue. So I can type SQS grep and then paste the number of the job. So it's already tells CG, which some abbreviation for job is being complete. So while it computes quicker than I speak. And if I repeat, now it is not there. So if the job is waiting in the queue, it's put letter Q in this place. If it is running, it puts letter R, and if it is about to quit, it is CG. Now I'm doing ls -lt, and you see it regenerated all stuff like outcar and walk pod and everything we needed. So I want to recreate, and I'm sorry for not making a circle because I don't want to hold you too long or do the whole process. So now I want to recreate states files that I needed for Spectra, and at the same time I can use them for density of states. So grep National Basketball Association outcar. So 64. Number of orbitals is different because it is a different version of us. So now here is the command that one can use to create states files. grep, and I know there were questions in the email, -a, and now I do a little math. 64 plus 4 will be 68. I'm looking for the keyword Fermi, and I don't remember if first letter is uppercase or lowercase, so I skip it. From the file outcar. And in case it was optimization and it was several replicas of list of orbitals, I take tail minus n number of orbitals, 64. And then forward it to the file states. Yes, let me copy this command to the chat line, and then I will answer your question. Please enter. Yes.
So why did you add 4 to 64? Sorry, I'm a bit lost.
Thank you for the question. If I so the keyword Fermi happens several times, and after Fermi, the list of orbitals starts in 1, 2, 3, 4 lines later. So the keyword tells show all lines after we see the keyword Fermi. And our constructive information starts 4 lines later. So I add 4 to the total number of orbitals. Does it make sense?
Yes, it does. Thank you.
Okay, yeah, and thank you for the question. Another way is just to copy this portion, create new file states, and paste it there. It's also legitimate. Okay, so let's check that states is healthy. Starts with 1, ends with 64. Copy states into energy POP, VI input overlap. So now the last line is 64, escape colon WQ. And now the names of the codes are slightly different on this server. So copy. So it's my personal cheat sheet, because from year to year I may forget names of my own codes. So if you are, I'm going to copy paste line by line, and everything will work. I promise. I did check it just before the class. But if you're curious, first line, this swap of modules, the code for oscillator strengths on this server, I did recompile it with lower level compiler, with GNU compiler. And by definition, they use Intel compiler. So I just swap the way how the instructions are connected, libraries are connected with compilers from Intel to the GNU. So I type this command. Then I copy, paste the executable, the actual executable from binary to here, and I can just give path to this executable anytime, but it is a little too long. It may be easier to just copy it into the directory, and it's not a big file. And then after it is ready, I just execute. So I can type ls-lt. And here, in addition to this input overlap, there are a couple of other files, including this oscillator strengths for CAM676. So I just need to launch this code, which is, I apologize for inconsistency with name, but it is basically the same as os dipole on the photon. So, period. Enter. And after executing this command, there is a file oscillator strength. Okay. So, sorry for taking a few minutes more. We'll skip round, but I'll finish so it will be logically complete. There is one more detail which is important if you plan to compute not only absorption by emission. For example, if I'm not encouraging anyone to change an advisor, but for example, if you want to transfer to the experimental group of Professor Eric Hobby or Professor in physics or Wen Kang Soon in chemistry, they experimentally measure emission spectrum. And emission spectra sometimes happen between unoccupied orbitals. If you short excitation higher up, it may emit radiatively between originally unoccupied states. So our original oscillator strength was including transitions only between one original occupied and one original unoccupied. But if we target to compute emission, we may need additional transitions. So the stuff that is computed here is more general. If I look onto OS strengths here, you see there are transitions from unoccupied to unoccupied or from occupied to occupied. In 90% of research, it is not needed, but to be ready for exotic research, it has this thing. But if you need only absorption, we need to find only those transitions that go from occupation 2 to occupation 0, and they are minority here. So this can be done in the following way. So I rename the oscillator strengths into oscillator all. Now I do not have file oscillator strengths. And then we extract only transitions that happen from occupation 2 to occupation 0. So number of lines in the O is 2000. Number in the strengths is 1000, a little less. More cos strengths. And now we have transitions from occupied to unoccupied. So we see OS strengths. Thank you for investing time. I'm about to finish. It's a few more comments. So number of transitions 1024. The number of HOMO is the same, 32. So I can practice the spectrum. So basically convert discrete set of transitions into continuous line. Number of transitions, 1024. Range, okay. 1, 2, 7. Line width 0.005. Number of HOMO 32. Done. LS minus OT. So it did recreate the file spectrum. And now I can practice the same commands to convert spectrum into continuous line. TS to GNU to the bin of SPE, and SPE underscore none. We do have this files with spectra in PostScript format, and I convert them ES to PDF WR SPE.ps SPE underscore nanometer. So that's my certificate. Files are ready, but I need to transfer them back to Photon and then to my directory. So how do I do it? And I understand that it's too much excessive information without practice. So I'm going to the very beginning when I was transferring information from, I have a quick idea. So I will move SPE PDF as SPE NERSC.pdf. And the same for spectrum as function of nanometers. Now I'm browsing up to my history of commands to the place where I was transferring files from Photon. Yes. And now I will just I will invert this command scp everything ended as PDF into given Photon blah 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 into this directory. And copy this command into the chat line. Paste. And here I click enter and type the password. So it transfers these PDF files. And then if I look into the files on the Photon, which I can access by this drag and drop, you see this SPE NERSC. And it just little, it defines the range a little bit different, but it has the largest peak on 3.3, right? And if I look on this SPE nanometers, also 3.3 nanometers would correspond to 430, 3.3 electron volts corresponds to 430 nanometers. Whew. Done. It's not all what I was planning. We didn't do heating, but I thank you for investing additional 12 minutes of your precious time into the course. So meeting is done. Everyone is welcome to department disconnect. I'll stay here and answer any questions.
Thank you, Dr. Killian.
Oh, thank you, Lola.
I was very
Yeah.
lost towards the end of this class, but I'll just watch the
Me
video.
too, me too.
I didn't understand anything.
I did speed up about five times quicker, and I understand that it is not good pace, but I'm trying any possible effort so that we keep as much as possible time for actual projects to speed up learning and then invest more time into projects. And if you really want, we can start them in like 2 weeks from now. If you want, we can maybe use 1 more week to solidify our skills in VASA. But when we will be doing projects, we can also keep learning some different things. And I have forgotten. Please remind me maybe during the class on Friday, or find yourself. There is a VASP manual available online by creators of this software. I'm trying my best to communicate on the most important basic things, but there is like about 200 pages available online, and it shows all little details about philosophy and practical aspects of the software. Okay. So feel free to depart or feel free to ask questions. I'm at your disposal.
Okay, thank you. Good night.
Thank you. Good night.
Mhm.
Thank you, Dr. Lee. Have a good night.
Good night. Good night, sir.
Random session that's unrelated
So it's about class.
unrelated to what we talked about today.
Okay, then let's wait if there will be class related questions,
That's
and then I'll stop recordings and
Professor, can you hear me?
yes, I can.
Okay, so you showed so many things, so I'm not able to follow those steps. I'm just watching that what you wrote in the MOBA text. So when you will upload this one, or could you please show me the screen, then I will take a screenshot of that one, then I will try there, because I don't want to do the same things again. Because I'm not able to follow the steps.
Okay. Do you think that video recordings will be sufficient, or you need the just screenshots of our command line?
A screenshot shot of the command line. So just go up. You started from the remove dot ps. So you started to
Oh, I can just like copy everything we did today and just send it as a file to everyone, right?
Yes. So from
yeah, that's pretty cool.
Okay. I'll just do everything.
Oh, then it's fine. Copy all.
Yes. It will be just quicker.
Yeah,
okay.
paste.
Does it want to paste?
I don't
Maybe it's
think
too much. Let
you
me
need to
maybe
open a Word
no.
file or something.
Yeah.
Notepad. Okay.
Okay. Yes. Desktop.
Yeah. Okay, then it's done.
Okay. Is it what you suggested?
Yes. And then now I will do the rest of the part.
Okay.
Okay.
Very good.
Thank you
Yeah.
so much.
Thank you for your patience. I understand that we kind of did pedal to the metal to speed up.
Okay. Bye, Professor.
Lina?
Yeah, I'm just trying to finish.
Okay. Yeah.
Get the file.
Steven, anything related to the class? So if you don't mind, I will stop recording, and after that